Especially if you can make it full screen, this will look much better.
Завтра как? Я буквально когда можете я там вам что-то в 11 дам знать, потому что я просто обалдела уже от хождения сюда.
And can everyone see my cursor on the screen?
I think so. I cannot say that I'm sure that I can see your cursor, but maybe it's a bit small, yeah?
Okay.
Can you at least make it full screen and then I will tell you for sure?
It should be full screen. Is that not what?
Well, it's not exactly full screen. It looks like shows a slide and this list of slides on the left.
Okay. Sorry, let me try again. I have multiple desktops. I think it was sharing the wrong.
Yeah. And also, I have asked you in email, are you okay with the live streaming and stuff like that?
Yes, that's fine.
Okay, very good.
Okay.
Well,
okay.
Yeah.
Now,
and we see your
screen.
cursor currently. Yeah.
Okay.
Irina, should we wait 1-2 minutes more? It's already like
please.
it's late, actually.
Okay, now I'm on place, yes.
Okay.
How many people we have? Not too much, but we can wait.
They're coming gradually.
They will come immediately. Richard is here.
In general, I would say we can start because it's already.
Yes, I think we can start.
Minutes. People will come gradually.
Yes. Hello, everybody. Let's start our seminar. Today we have a pleasure to listen a talk by Leah Jenks. She will tell us about runaway gravitational production of dark photons. 1 hour, please.
All right. Thank you so much for the introduction and for the invitation. Good morning to everyone in the US. Good evening, afternoon to those in Europe and elsewhere. And yeah, I'm very excited to be here to talk to you about runaway gravitational production of dark photons. So this is going to be more focused on the all of that part of the quantum gravity and all of that. And we can go ahead and get into it. And I'll also say that everything I'm going to discuss is in collaboration with Rocky Cobb here at the University of Chicago, with Evan McDonough at the University of Winnipeg, and Christian Capinelli at McGill. And then this talk is going to be based on the following 3 papers, mostly on these first 2, the second of which will be out hopefully sometime in the next couple of weeks. And then at the very end, I'll mention a little bit as well this paper from last year. Okay, great. So before we get into the talk, I will just lead off right away with some of the main takeaways. So I will be talking about gravitational particle production as a production mechanism for dark matter, but also just as a generic mechanism for particle production in the early universe. And I'll discuss how we can produce specifically dark photon dark matter via this mechanism. And then I'll discuss how we can add non-minimal couplings to gravity between the dark photons and gravity during inflation, which can lead to many instabilities in the theory, specifically ghosts and what we call this runaway instability. However, we do find that there is a kind of stable region of parameter space, which avoids these problems, and then we can really kind of consider this dark photon as a dark matter candidate, excuse me, in this parameter space to get the correct relative abundance today. And then at the very end, I'll show how these same results for dark photons can be equivalently applied to understand gravitational particle production of Kalb-Raimond-like particles. Okay, so my kind of obligatory what is dark matter slide. So the short answer is that we, of course, have no idea what dark matter is. The slightly more detailed answer is that we know that it makes up about a quarter of the energy density of our universe today, where the other 75% is the baryonic matter and dark energy. And there are kind of a menagerie, a zoo of different theories of dark matter that have been proposed over the years. And so I really always like this figure by Tim Tate, which kind of just shows not even all of the dark matter candidates, but some of the types of theories that have been proposed. And these all kind of have different motivations and different levels of being ruled out by experiment. But the parameter space of types of theories that can be considered is really quite wide. And another way that I like to think about how little we know about the dark matter problem is thinking about this in terms of mass scales. So the kind of standard paradigm for what people have thought about dark matter as for a long time is the WIMP, or the weakly interacting massive particle, which can be on the order of GeV to a TeV. On the very light end, we can think about ultralight axions as dark matter, which can be as low as 10 to the minus 22 eV. And then there are even, theories where people have posited that black holes could be some of the dark matter, which could be up to, 10 to the 4 solar masses. And so in all, this is something like 90 orders of magnitude in mass, where we could have a dark matter candidate. So this is really trying to find a needle in a haystack. And so just to emphasize that it's really important to kind of fully explore the parameter space of potential dark matter models and kind of understand phenomenologically their behavior. Okay, so there are a variety of different ways to produce dark matter. The one that I'm specifically going to be focused on is gravitational particle production, or cosmological gravitational particle production, that I will also shorten to GPP throughout the rest of the talk. So this is a very old idea going back to Schrodinger in the 1930s. And effectively, what is happening is that the expansion of the universe during inflation leads to particle production. And specifically the fact that the expansion of the universe is so fast and non-adiabatic essentially pulls particles out of the vacuum. And so the way that we can understand that in terms of just kind of basic quantum mechanics is by considering two sets of operators that we have, one set at early times and one at late times. And so here by early times, I'm referring to kind of the pre-inflationary period, and then late times will be post-inflation. So not late times as in our current universe, but post-inflation. And so if I have these two operators and I have the vacuum of some field before inflation, I can act the early annihilation operator on this vacuum, and I just get back 0, as we usually expect. But throughout inflation, in this kind of Heisenberg picture, these operators are evolving. And so the late time operators are not equal to the early time operators. And so we have, if you act the late time annihilation operator on the same vacuum, you don't get back 0. And in fact, this is what is then corresponding to particle creation during this epoch. And so we can think about the particle number created as an integral over k, where k is the wave number, and then this inner product of the late time operators with the early time vacuum. And so we can relate the early and the late time operators via a Bogoliubov transformation. So we have these two parameters, alpha and beta here, which we refer to as Bogoliubov coefficients, that we can use to connect the early and the late time operators. And so from these expressions, we can obtain the particle number density, the number density spectrum as a function of k in terms of this coefficient beta. And then from nk, we can determine the co-moving number density as the integral over k of this spectrum. And so, of course, I have skipped many technical details here. There's a really nice review by Rocky Cobb and Andrew Long that came out at the end of last year that goes through more of these technical details if you're interested. But it's been shown that GPP is an effective.
Excuse me, there is some small question maybe.
Oh, sure.
Philip, please.
Yes, Leah. You can write the de Sitter metric in static coordinates. So how do all these effects work in that case?
So in this case, yeah, that's a really good question. So in this case, we consider basically the inflationary epoch as going from some quasi-de Sitter phase into either kind of matter or radiation, depending on your reheating model. And so most of kind of the action here is happening in the transition from the end of inflation into matter or radiation.
So this is really related to the graceful exit.
Excuse me? Sorry, say that again?
It's the graceful exit.
Right, yes. It's most of the particle production is happening kind of at the very end.
Okay, thank you.
Mm-hmm. Yeah,
excuse me, may I ask you maybe another short question? Maybe it's very naive. This Bogoliubov transformation, is it how to say, is it certain that it always exists? Because it also should be unitary, yeah?
Mm-hmm. That's another good question. So I think at least in this case, in this particular connection of these operators during inflation, we can be confident that it does exist. But it is possible that kind of more broadly it may not. But in this scenario, it does.
Okay, thank you.
Yeah, any other questions so far? All right, great.
Please continue.
Okay. Thanks. Yes, so as I was saying, it's been shown that this mechanism can produce dark matter in the kind of correct relic abundance for a wide range of masses and spins. So this works kind of for scalars, for vectors, as I'll show, for spin 3/2, even some higher spin models, spin 2. You can really get a wide variety of dark matter models that are produced this way. And what I also want to emphasize here is that this is a totally generic process that I'm describing. So here I have not added in any additional physics. The only ingredients are that I have inflation, I have some inflationary period, and I have some kind of spectator field. So I have some field that is not the inflaton, but is also around during inflation. And I'm not adding in any extra physics or requiring that there be kind of any other interactions, things like that. This is a totally generic effect that we expect to happen, whether you want it to or not. So it's a nice way to think about dark matter production from that perspective. Okay, so now we have talked about producing dark matter. So let me now focus on a particular candidate. And the one that I'm going to be talking about are dark photons. And so dark photons in this regime, I'm going to be referring to specifically a massive spin 1 field or a Proca field. So I'll use these terms interchangeably. But what I'm referring to when I say dark photon, spin 1, or Proca is the following action. Where here F mu nu is just the field strength of some massive spin 1 field, A mu. So of course, this is very similar to the normal electromagnetic Lagrangian that we know and love, but we now have this addition of a mass term because we would like to consider this as a dark matter candidate. And so in the context of dark matter, people think about dark photons in a couple of different ways. So it's very often considered that dark photons are a portal to the dark sector. So you can, for example, obtain kinetic mixing with a standard model photon, where you can have an interaction in your Lagrangian, which looks like this, where you have a term which mixes the field strength of the dark photon and the field strength of the standard model photon with some coupling parameter epsilon. And then in this case, the dark photon would also couple to some additional dark matter candidate and then kind of act as a portal from the standard model to the dark sector. But we can also think about dark photons as a dark matter candidate kind of in their own right. So it's been shown that they can be produced by a freeze-in in the early universe. There has been some work by Graham in 2015 and then Cobb and Long again 2018, or excuse me, 2020, looking at gravitational particle production from the dark photon, this free theory. And it's been shown that that can produce dark matter in the kind of correct relic abundance. And there are also a variety of other early universe processes that can produce dark photons, like misalignment, for example, a nice paper by Nelson and Schultz from about a decade ago. And of course, this is not an exhaustive list of production mechanisms. So if I have left off your favorite dark photon production mechanism, I apologize. This is just an example of some of the ways that these particles can be produced. But as I said, we're going to focus on GPP. Okay, so the previous slide that I showed, we just had these first two terms, the free theory, but we're also, it's also possible for this dark photon to have non-minimal couplings to gravity. So there's two additional terms that I can add which obey the symmetries of the theory. So here I've added a term where I've coupled the dark photon to the Ricci scalar. And then here I have a term which couples the dark photon to the Ricci tensor. And then I have two dimensionless coupling parameters, Xi1 and Xi2. So if I set Xi1 and Xi2 to 0, I return back what we call the minimally coupled theory, and this has been previously studied. But I want to emphasize that in addition to just being able to write down these operators, which again are allowed by the symmetries of the theory, we also expect that these operators will arise from loop corrections to the mass vertex, as well as if you turn on things like self-interactions. So it is really very general to add these operators, and we in fact expect that they should be generated if we want to consider this kind of full theory. And so with that, the two questions that we would like to ask are first, how does the addition of these two non-zero parameters, Xi1 and Xi2, impact dark photon production via GPP? And so I should also mention that there were two nice papers that came out last year that did discuss this question in a nice way. Those papers were a little bit more limited in their scope. They were just looking at particular regions of parameter space. So we're interested in kind of exploring this whole parameter space in Xi1 and Xi2. And so then the second question is, as we will find, adding these parameters can cause some problems in the theory and some instabilities. And so we would like to explore the parameter space and determine what are the kind of allowable values such that we can both avoid potential theoretical instabilities in the theory, as well as produce the correct relic abundance of dark matter from in a phenomenological aspect. Okay, so the biggest effect of adding these two couplings is to lead to a time-dependent effective mass, which you can kind of appreciate just from the form of the Lagrangian. But having these two terms leads to two different effective masses, which I will call mt squared and mx squared. So here, m squared is just kind of the particle mass itself. And then it has these additional terms where there is a coupling to r, some dependence on the Ricci scalar as well as H, where H is the Hubble parameter throughout kind of the evolution of inflation. And so what you'll notice here is the now mt squared and mx squared are time dependent. So R and H are both evolving throughout inflation into matter and or radiation domination. And so these masses are now also evolving in time. And this is going to be kind of the cause of the effects that I'm going to discuss shortly. Okay, so skipping kind of some technical details, this is a massive spin-1 field, so it has 3 degrees of freedom. There is a longitudinal mode and then 2 transverse modes. For the rest of this talk, I'm only going to discuss the longitudinal mode. In gravitational particle production, that ends up being the much more dominant mode of the field. And so we're not going to worry about the transverse mode. So everything I'm going to say from now on is just about the longitudinal mode. But one can decompose a mu in the previous way, and then decompose into the longitudinal and transverse modes, and then further decompose into mode functions to get the following expression here. So we've now written the action in terms of these effective masses, mt squared and mx squared. And then I'll also just point out that A here is the scale factor, and then eta is conformal time. And so from this action, we can go ahead and canonically normalize it by defining this parameter chi in terms of kappa, where here kappa is defined in the following way in order to canonically normalize the kinetic term. And so from here, in terms of chi, these mode functions, we obtain the following kind of very nice looking form for the action. And so here again, this is like very nice looking, but here this omega squared is actually hiding a lot of complexity. So we have this kind of very complicated looking expression which is dependent on M, on H, on R, as well as the derivatives of H and R through the derivatives of these effective masses. And so this is quite complicated, which I just show to kind of emphasize that there's a lot happening here. But really, the main term that we're going to be worried about is actually just this first one. So the thing to notice here is that omega squared now has a modification to the sound speed, which we define as this mx squared over mt squared. So we will return to that momentarily. Okay, so now we want to think about what potential instabilities we can have now that we've added these terms. So as I said before, these effective masses are evolving throughout the inflationary period, and they're also not necessarily going to be positive definite. So R in particular oscillates through the end of inflation into matter or radiation domination. So we expect the effective masses to vanish. And so from the mode equation, we can see that there's potential for a wrong sign in the kinetic term as well as a wrong sign in the mass term. So let's look at each of those in turn. So first, I'll talk about the kinetic term, in particular, the possibility to have a ghost instability. So here, when I'm referring to ghosts, what I mean is a theory that has the wrong sign kinetic term. So it has a negative sign. So from our definition of kappa, which we use to canonically normalize the field, we can see that it has the following form again. So to avoid ghosts, we would like kappa squared to remain positive throughout the whole evolution where we're considering this particle production. And so, of course, this ends up being a k-dependent statement because for very high momentum modes, even if mt squared is negative, if it's negative and smaller than k squared, then kappa squared will still be positive. But we would like to make a k-independent statement, which can be applied to arbitrarily large k. So in that case, the most conservative thing to do is to take require that mt squared be larger than 0 throughout, again, the whole evolution where we're considering particle production. And so if I want to now think about the parameter space where that is allowed, I find the following. So here is just showing kind of an example of C1 and C2 in kind of the limiting case where mu, which is defined as m over he, is much, so where m is much, much less than he, where mu is m over he. Of course, we want to consider, larger masses, but just to get some intuition for the kind of regions of parameter space that we are thinking about, we can think about it this way. And so we can see that 0, 0 is, of course, a fine point because that's the minimal coupling. And then we see that the ghost-free region kind of carves out this wedge in the upper left-hand corner of the parameter space. And so anywhere in this region, the theory will be ghost-free, and we're able to kind of study it as we would like. So we need to remain in this region. Was there a question?
Yes.
Yes, I would be happy to ask you if you permit. Look, I'm a bit confused. You say that you want to make a statement for arbitrary large K, but your theory looks like an effective theory. In a sense, it should have some cutoff. Why do you care about arbitrary large K?
Yeah, so in practice, we we don't actually need arbitrarily large K, but perhaps a more precise statement is just that this is the most conservative thing we can do. So of course there is, up to some K, you could still allow this to be negative. The most conservative thing is to just require that mt squared must be positive. So that's
okay.
the approach we take.
Okay, thank you.
More precise way to say that. Any other questions? Okay, great.
Okay, please.
Okay. Oh, sorry, was that another question?
No, thank you.
All right, so we've talked about ghosts in the kinetic term, but there is also another instability, which has to do with the mass term. So of course, when I have a mass term with the wrong sign in my theory, that's a tachyonic instability. So here I have written down again this form for omega squared, where I have kept the kind of first two relevant terms, and then I have put all of the other complexity into just some function f, because we're not going to worry about that. And so actually, when I have omega squared less than 0, this is not necessarily a problem. So having a tachyon in this theory is not necessarily an issue. And it's in fact been shown that having this effect where omega squared is less than 0 leads to an overall enhancement of the particle number being produced. And so this can actually be a useful thing if you're trying to produce kind of more dark matter. However, as I mentioned before, omega squared also has a modification of the sound speed, which is defined as this mx over mt. So of course, in the minimal theory where C1 and C2 are 0, the sound speed is just 1. And so we have no problems with this. But in this case, excuse me, we now do have this modification where the sound speed is also evolving. And so we have required that mt squared be larger than 0 to avoid ghosts, but we have not said anything about mx squared. And so what we will find is that allowing the sound speed to be imaginary, or cs squared to be less than 0, actually leads to runaway production of the dark photons, which ends up being problematic. And so a way to kind of understand that is by looking at the evolution. Here is omega squared as a function of scale factor. So here A equals 1 corresponds to the end of inflation. And so back to Philip's question earlier, most of the action is happening kind of in this transition out of inflation. So here in this blue, I'm showing the minimally coupled theory. So this is C1, C2 is 0. And so we can see that at relatively low K, it does indeed oscillate throughout, oscillates, becomes negative, oscillates a bit, and then increases. And then as we go to high K, omega squared just is dominated by K squared. And so we can see that it's just up here. It's perhaps a little hard to see on this plot. Similarly, if I take values of the non-minimal couplings that are very, very small in the ghost-free region, which you can see is this green curve, I have very, very similar behavior here, where it oscillates a bit and then just goes like K squared at higher K. However, if I go to this red curve, where I have now chosen values for C1 and C2, which are ghost-free, we can see that there is a much larger effect where there are these kind of severe oscillations. But this is not actually a problem. This is okay. But we can see that at high K, I'm still oscillating through 0 as a result of CS squared being negative at some point in this evolution. And therefore, I don't have this kind of asymptote to omega squared as K squared. And so I can think about particle production being corresponding to every time this omega squared oscillates through 0. So this oscillation, both in going negative and the magnitude of it, you can think about this as like a burst of particle production. So for the blue and the green curve, we're getting some particle production here. And then as we reach some very high K, it kind of shuts off. Whereas in this, for the red curve, it doesn't. It continues to oscillate and you continue to get particle production. And so we can kind of appreciate that by looking at the spectrum of particles produced in K. So here again, I'm showing the same values for that blue curve and the red curve. So the blue is the minimal coupling theory. So this is what we kind of expect from previous work. And then the red is what happens when we have this runaway effect. And so you can see, K is 10 to the 1, which is not very high K at all. This is, 15 orders of magnitude already increase compared to the minimal theory. And so this is a problem. First, if we want this to be dark matter, because of course, kind of the abundance of these particles produced has to be within some particular range. But also, if we want to not, overclose the universe with dark photons, this has to be kind of regulated or controlled in some way. And so we would like to do that as well by requiring that the theory remain runaway free as well. And so in order to avoid the runaway, we have to require that the sound speed squared remain positive, similar to what we did before. So we've already required that mt squared be positive to avoid ghosts. So now we have mx squared is positive to avoid this runaway. And so in this m much less than HE limit, this carves out a region of parameter space right here in this kind of lower right-hand quadrant. And so what you'll notice is in this very, very small m limit, there's actually no overlap between the ghost-free and the runaway regions. So the only acceptable parameter combination in this case is actually C1 and C2 are both 0. And so, of course, this is just kind of representative. We would like to consider very, very small positive masses. And so fortunately, there is a region, which we call this stable region, where there's no ghosts in the theory and there's no runaway, where the theory is well behaved for larger masses. So here on the left, I'm showing this overlap region for m over HE is 0.1. So you can see that there is this very, very small region here, which we kind of zoom in on in this inset here. And the yellow shaded region is where the theory is well behaved. And then over here, this is going to m over HE is 1. where we can see that the region expands to larger values of Xc1 and Xc2. But I'll also say that mu, where mu is m over he, the ratio, these regions remain the same for the ratio of Xc over mu squared. And so for the rest of the talk, I'm going to focus on particle production in these kind of stable, safe regions where we avoid these potential problems with an eye towards thinking about kind of dark matter phenomenology and production. Okay, so before we get to that, I just want to mention a few potential solutions that one might think about to solve this runaway problem. Yeah, another question.
What is the question? Yes.
Yes. Since the masses are time dependent, you can have this stable region, but it can still evolve in time into something unstable.
Yes, so this is a really good point. So the way that we described the stable region is to look at the full evolution in the particle production that we're considering and requiring that it becomes unstable at no point in the evolution.
Okay.
So yeah, so
this means ever stable.
Correct. Yeah. So this stable region is always stable. So that's how this has been defined. So even if something starts stable and then evolves into one of these regions, then we don't consider it at all.
Okay. Thank you.
Yeah, you're welcome. Yeah. So again, this is kind of the most conservative choice that we can make. Yeah, but that's a great point. Thanks for bringing that up. Okay, so right, so let me just quickly review a couple of solutions that one might think about to resolve this. So the first is, of course, that this is an EFT, as was mentioned before, and so there potentially needs to be some cutoff for the theory. But if one goes back to look where this really this runaway starts taking over, this is a relatively low K. The end of inflation really corresponds, the modes that are relevant here are really around K equals 1, where this is already significantly enhanced compared to the minimal case. And so if we take even that as the cutoff, then we aren't able to do perturbation theory during inflation. So you can, of course, take some cutoff, at the Planck scale or some other reasonable scale like that, but then you still have a lot of particle production before you get there. One could also consider some potential UV completion, but it's not even clear that in a UV complete theory, this problem will be solved. We still expect to generate these types of couplings that will generate these instabilities. And then lastly, I'll just mention that there was a nice paper a few weeks ago by Anna Maria Hell, which looked at attempting to resolve this by adding a disformal coupling to gravity. And so this is a nice solution with a few caveats. So it does, it's a modified gravity theory. So you take the metric and shift it by a factor which removes the coupling to the Ricci tensor, which ends up being this kind of problematic one for the runaway. And so it removes this at tree level in this modified gravity theory, but it's not actually clear that it does remove it when you consider kind of the one loop level and more terms in your EFT. And so this is kind of a nice solution in a limited regime, but doesn't fully solve the problem. So it does seem like this is a problem that we really have to avoid by just kind of being choosing our parameters not in the runaway region, so in this stable region. And like I said, that's what I'll focus on for the rest of the talk. So now we're going to discuss this particle production only in the stable region with an eye towards dark matter. So here I'm showing again the particle spectrum as a function of K for a variety of different choices of the non-minimal couplings. So here the blue in both panels is again the minimal in order to compare. And then here I've just turned on Xc1 and I've set Xc2 to 0. And then on the right, I've taken this green curve, which is a little bit hard to see in this plot, but I've taken this green curve and then fixed that value of C1 and then varied C2. And so what we can see here is that the biggest effect is the emergence of this second peak in the spectrum. So for the minimal coupling, we expect that there's a peak around K is 0.1, where the particle number is maximized and then kind of falls off again. And so we can see that we do still have that same peak, but we also have an additional peak that occurs around K equals 1. And so this is because we have these additional terms in our in omega squared as well in the frequency. So here for C2, this is not actually caused by the sound speed. The sound speed is 1 in all of these cases where C2 is 0. But because we have those 4 or 5 additional terms in omega squared, we get the second peak here. And because we determine our kind of total particle number by integrating over this region, we can see that this is going to lead to an enhancement in the particle number depending on your choices of the couplings. And then similarly, if I take C1 fixed and now vary C2, there is again some variation in the parameters, but mostly remains the same with this kind of second peak. And I'll also say here that the region that we're considering is also strictly where the sound speed is subluminal. And so again, I'll just show here. So that region that I showed was a little bit triangular. And then here we can see the evolution of the sound speed, again, throughout the inflationary period for several different choices of the parameters. And so this red curve here, you can see that there is a region that is both ghost-free and runaway-free, but where CS is superluminal, corresponding to anything where C1 is negative and C2 is positive. And so in order to avoid that effect as well, we will restrict ourselves to only subluminal values of CS. So anything that puts us in this kind of lower region here. And that corresponds to this region of parameter space here. This is just an example of mu is 0.1. And so what we're showing in this plot is the minimum value of CS. So we can think about kind of characterizing the effect of the sound speed by thinking about how large this first oscillation is. So here we can see, again, the minimal coupling, sound speed is just 1. There's no oscillation. As we slowly turn on the non-minimal couplings, in this yellow, there is a little bit more of an oscillation. And for the green, it's now much, much larger, down to minimum CS is about 0.6. And so that's what we're characterizing here on the right. So we can see that for C2 is 0, the sound speed just remains 1. And then as we go out further and further into the parameter space, this oscillation gets larger and larger, out to about 0.005 is this very, very edge here. And so, of course, once you cross this boundary into the white region, you enter into a region where the sound speed is potentially negative, or the sound speed will go negative at some point, and therefore run away. So we restrict ourselves to that. But you can get very, very close to CS is 0 in this region. And so this is the region of parameter space where we would like to explore how the dark matter production is affected. And so the way we do that is by taking contours of constant CS from the previous plot. So here, this is constant minimum CS. So this is 0.9, 0.7, 0.5, 0.3, and 0.1, just kind of as representative examples to explore the parameter space. And from these contours, we calculate the relic density today, which is parameterized by this factor omega h squared over 0.12. So this is, of course, dependent on the mass. It's dependent on HE, which is again, the energy scale at the end of inflation. And it's dependent on the reheat temperature, as well as the particle number. And so for this plot here on the right, which is showing this omega squared, omega h squared parameter, we've just kind of taken fiducial values for HE and T reheat. We've taken HE as 10 to the 12 GeV and T reheat as 10 to the 6 GeV. But these are really kind of dials that one can turn up and down to get the correct dark matter abundance. And so to obtain the relic density today, we would want this fraction omega h squared over 0.12 to be approximately order 1. And so what we can see is that really tracing out these contours of the minimum value of CS, we get more and more particle production as we go towards the edge of the boundary. So here, this is kind of order 10 to the 2. And then as we go out to the edges, the particle production that we're getting in terms of omega h squared is really 10 to the 5. So we get an overproduction in kind of deeper into this parameter space as compared to the minimal theory. And so again, this is 10 to the 5, but one can kind of move these parameters up and down as well as the mass to get kind of the correct abundance. And the other thing that I'll mention is that this opens up the parameter space even more compared to the minimal theory. So for the minimal theory, again, the particle production is fixed, but here we're allowed to have higher particle production, which allows us to go to, for example, lower H and lower masses in order to get the correct relic abundance. So in this region, you're able to get masses that are in a much wider range than you can for the minimal theory. So for the minimal theory, for example, this can produce particle masses as low as about 10 to the minus 7 EV. But for HE is like 10 to the 14 GeV. And so now that we have this potential kind of overproduction, we could push down that mass range even further, 2 or 3 orders of magnitude, or get particles which are order, 10 to the minus 6, 10 to the minus 7 EV for much lower scale inflation. So this really kind of opens up this full parameter space for the types of models where this works. So that's a really nice kind of bonus of doing it this way. In addition to being able to get the correct amount of dark matter, it opens the parameter space. Okay, so for the last few minutes of the talk, I'm going to shift gears a little bit and discuss Kalb-Ramonde-like particles and how everything that I have said previously can be applied to these other particles, Kalb-Ramonde-like particles, which are we can also think about as a dark matter candidate as well. So the Kalb-Ramonde field is this antisymmetric two-form field, B mu nu, which has the following action, where it has this mass term, B squared, and then it has a three-form field strength, dB. And so the Kalb-Ramonde field often occurs in the context of string theory. And often people think about the Kalb-Ramonde as either being massless, in which case it's dual to an axion, so it's literally just an axion, or being massive, but with a mass at the string scale. So, not relevant for our kind of everyday physics. However, it's also very reasonable to think about kind of an EFT-inspired B mu nu or a B mu nu-like object, which can kind of generically appear as a valid representation of the Lorentz group that we can think about kind of an intermediate mass region. And so these are these Kalb-Ramonde-like particles that I'm referring to, are these massive B mu nus with some mass that's in between 0 and the string scale. And so the Kalb-Ramondes have this really nice property where they have these duality properties. So as I mentioned on the last slide, if the Kalb-Ramonde is massless, it's dual to a axion, to a massless axion, excuse me. But when it's massive, it actually becomes dual to a pseudo-vector field, which you can see in the following way. So if I take the Kalb-Ramonde action and I decompose B mu nu into components, I find that I get back a pseudo vector component that is exactly the Proca action. Is exactly this action for a massive spin 1. And so this is again with no non-minimal couplings, but you can even see at this level, everything I have said for the massive spin 1 can also now be applied to a massive Kalb-Ramond. And so some previous work with myself and the same collaborators, we showed that for GPP, this actually remains the same because, of course, this is a process that doesn't depend on parity. But if you consider things like Friesen, here you can have an axial coupling for a pseudo vector that you, for example, can't have for a vector. So there could be other differences there.
Oh, excuse me, there is a question. Yes, Kiri, please ask your question.
I may be mistaken, but isn't the upper action with the H and the B, isn't it gauge invariant?
Excuse me. I think this also explicitly breaks gauge invariance.
Oh, you can't write it as d mu a nu minus d nu a mu?
No, so here so B mu nu here is the field itself.
Oh, I see. And then and these things can arise in string theory, I think you said?
Yes.
So does that mean that string theory is not gauge invariant?
So I think in string theory, so this is the like 4-dimensional action. I will say I'm not a string theorist, but my understanding is that when these arise in string theory in the full kind of 11 dimensions, it's all fine.
So it's possible that the compactification down to 4 dimensions destroys some gauge invariance. Because if that's a case, then I think you can make a stronger argument for the m squared a mu a mu.
Mm-hmm. Yeah, I mean, I will also say here you can perform the kind of Zuckelberg trick as well to get this in terms of a massless field.
Thank you.
Excuse me, maybe I make a general remark. Of course, in string theory, there are massive gauge field where not belong the massless sector. In high level, of course, there are many, infinite number of vector field with some mass. It does not contradict anything, but this is, you cannot, of course, construct the gauge theory just with mass as written here in 4-dimensional case, but then this sphere is isolated. But if we add some interaction, no problems. So everything, from my point of view, everything is okay. What Leah says, okay. Okay, maybe we can have this discussion after the talk. Yes, please.
Great, yeah, thanks for that clarification.
Mm-hmm.
Okay, so this is in the minimal case. And so we can do the same thing if we think about adding non-minimal couplings. So for the Proca theory, again, we had these couplings, Xc1 and Xc2, where we coupled to the Ricci scalar and the Ricci tensor, leading to the following effective masses. Now for the KRLP, for the Kalb-Ramond, we can once again couple to the Ricci scalar, with this b squared, but then we can't end up coupling to the Ricci scalar, or the Ricci tensor, excuse me, due to the symmetry properties of b mu nu, but we can couple to the Riemann tensor, which has the following form. And so now we have these couplings C3 and C4, and the following form for the effective masses. And so what you actually find is that one can just rescale these coupling parameters and find that the effective masses are the same, at least on FRW, which is the kind of background that we're considering for GPP. And so what we get from this is that even in the non-minimal theory with these additional coupling terms, we can also obtain the GPP of chalbromones, again, for free from our analysis of the spin 1. And so as I mentioned earlier, I'll just emphasize there are other production mechanisms where you would see a distinction between these two. For example, via freezing, you could couple the chalbromone to different fermion currents than you can for the dark photon. But in terms of GPP, the two theories are identical. And so that's kind of a nice result we get for free as well. Okay, so I think I will just wrap it up with my summary and conclusions. So as we've discussed, we've talked about adding non-minimal couplings to gravity for a massive spin 1 field, which can lead to ghost and runaway instabilities in the context of gravitational particle production. However, in the kind of ghost-free, non-runaway, stable region of parameter space that we've identified for these non-minimal couplings, one can obtain the correct relic density of dark matter for kind of a wide range of theories the addition of these non-minimal couplings allows for lighter masses and a larger kind of suite of inflationary models that we can consider in order to produce the correct amount of dark matter. And then lastly, I've just mentioned that our results can also be applied to chalbromone-like particles as well. And so with that, thanks so much for your attention, and I'm happy to take any other questions.
Okay, thank you very much for your very clear explanation what is going on. Questions, please. Yes, Alexei first. Yes, please.
Okay, thank you very much. Thanks for this very interesting talk. I have perhaps a couple of questions, and the first of them is quite general. So as I understand, you want to couple this already during inflation, yeah? So it looks like on top of this, also inflation is going according to some scalar field, yes?
Yep.
Am I correct here?
Yep.
Then my question is very simple, actually. This coupling to extra field, does it somehow affect inflation?
Yeah, so that's a good question. So in this case, we're not considering any kind of back reaction of the production back onto the inflationary model. So everything I've showed, we just considered just kind of a basic quadratic inflation model that then kind of evolves R and H. But this is pretty general. The results are very similar for other types of models as well. One could also consider kind of the effects of this particle production on the inflationary dynamics, but generally these are quite small effects. So we kind of say
no, it's not about inflationary dynamics. Dynamics, okay, let it be somehow, but you include a vector. In inflation, we usually use 1+3 ADM decomposition. Vector, which looks like a variant vector, will contain a scalar degree of freedom, which will, this other way, join inflationary scalar and will affect CMB. The question is, will it affect enough to be observed, or maybe it will affect such that it contradicts CMB? This question.
Oh, I see. That's your question. Yeah. So in this case, again, we consider just like working in the regime where this is not affecting kind of adding on to inflation. We assume that inflation happens, and then you also have this kind of spectator field. So it's in the regime where it's not affecting the CMB, because yeah, of course, if you had big modifications, that would be highly constrained as well.
Yeah, but I cannot say that I understood what is controlling how much it couples to inflation. But anyway, since you say that you didn't consider it, maybe you indeed didn't consider it. And another question which I have is like this. You have two couplings, Xi1 and Xi2. Xi2 is a bit tricky, but Xi1 is just R multiplied by square of vector field. Don't you consider just remove this coupling by conformal transformation and see what happens next?
Yeah, so that's very similar to the approach that Anna Maria took in, or sorry, you're saying to remove the R coupling or the
No, I mean just rescale metric. And when Xi2 is in place, then it is maybe a bit tricky. But if you have only Xi1, for example, which is just R a mu squared, then you can just remove this coupling. Well, not remove it, but rather make a conformal transformation, which will be a mu squared, and kind of rewrite your theory like GR plus something. And didn't you consider doing this?
Yes, so that is very similar to the approach that Anna Maria Hell took in her paper, which was to introduce this disformal coupling to remove this. And so, right, so in that case, you do end up with modified gravity. So you have, you know, G, exactly as you say, you have GR, you would have some other effects there. But it also, at least in her paper, which she showed, so it does remove this effect at tree level. But it's not clear that, you know, you wouldn't continue to still generate these couplings at loop order and things like that. At least in her paper, she just showed at tree level. You can do that, but it doesn't generically fix the problem. But yes, that's definitely kind of a pathway to a solution.
Okay, thank you.
Okay, where is the next question from Philip? Philip, are you here?
Yes, I'm right here. Yes, Leah, first of all, thank you for this nice talk. My question's a little bit related to Alexi's, not so much whether your C1 and your extra terms will modify inflation, but won't they result in a massive graviton? I mean, if I just write down the gravitational equations, I'm not going to just get the usual box H mu nu equals 0 because of all of these R coupled to a mu type terms. So won't it make the graviton massive?
Yes. So again, yeah, good question. I think related to Alexi's question. So again, we're considering this specifically in the kind of the regime where there's no back reaction. So if you kind of considered the full thing and you did want to then you would also modify Einstein's equations and you would get some kind of effective graviton mass. I think it's been shown previously that for these types of effects, for GPP, that's like a very, very small effect. And so we don't worry about it here. But in principle, that you're correct that you would have that.
And related also to Alexi's question, you can say that you don't have a back reaction because the inflationary piece itself is dominant. And that means a very big Hubble parameter, a big H. But if you make H big, then you're getting rather large masses for the dark photons. So I don't see how you can have a large H to make the inflation be dominant and at the same time not make the masses be as dominant and modify the geometry.
Yeah, so this is
the question you're asking.
Yeah, so this is a good point as well. So we also have, so you're correct that it generally will produce particles of order m over h, but you don't actually have to get particles that are strictly order h. You can also get much lighter particles. So even, for example, in the minimal case, you can obtain dark photons as light as m over h is like 10 to the minus 16 m over he. So there is a kind of a region, which is in particular the one we're interested in thinking about for dark photons, where there is kind of a hierarchy of scales between the two.
Okay. So I think for completeness, what would be nice is if you could show that region in parameter space that you've emphasized, where everything's stable and no ghosts, no runaways, also is one for which there isn't a large back reaction.
Mm-hmm.
I mean, and then you've closed the loop.
Mm-hmm. Yeah, thanks for pointing that out. I think that's definitely important to comment on as well.
Where is one more question, I guess? The question is from Savide. George, could you please ask your question?
Okay, thank you very much for interesting talk. I am just want to ask, maybe not very much connected question, but it is, I was thinking about the term, like you have Riemann tensor, like R mu nu lambda rho, and then with the electromagnetic F mu nu F lambda rho. Is that term was considered, or is it interesting, or what is that?
Sorry, so you said R mu nu
Lambda
lambda.
rho. On page 27, I think you have something.
27, yes.
Oh, yes. So, yes, you see you have this Ramond field, but you can write R mu nu rho sigma, and then just F mu nu F rho sigma. It will be interaction of photons with R mu nu lambda rho.
I see. Yeah, coupling to F.
Yeah, you have it in Ramond sector, but why not to add that term in with the vector fields?
Yeah, so that will end up being a higher derivative term. So here, this is coupling, this is like the equivalent of this term, because this is, right, so B mu nu here is the field. So B mu nu does not have any derivatives. So one could certainly write down Riemann, F mu nu, F rho sigma, but it would be a higher dimensional term than these.
What's wrong with that?
There's other ones you can add, but these are the lowest order.
I see. Okay, thank you.
Yeah, thanks for the question.
Okay. More questions, please? There is one question in the chat. Could you please read? Where is the dark photon where you are? Alexei, maybe for me, the text is very small.
Yes, of course. The question is if there are dark photon, the U1 is broken, but we know that U1 is always conserved. How to solve this problem?
This is maybe not related. Okay.
Yeah,
so
so I think this is kind of related to the point earlier about kind of gauge invariance with this. So the dark photon having, of course, a massive gauge boson does indeed break this UN symmetry. You can that does happen with the thing with the field, but you can also just do the usual kind of Stuckelberg trick as well to get back a massless degree of freedom.
Okay, Philip, you have...
If I can just comment on Huang Vu's question. I mean, we do produce massive gauge bosons in Weinberg-Salam. So it is possible that this particular A mu got its mass by some Higgs mechanism, which you didn't specify, in which case you would be completely compatible with gauge invariance.
Yeah.
Anyway, that's the
thanks.
Yes, I think you gave...
Yeah, I agree.
Yes, you gave a very clear explanation. Okay, more questions, please? If not, thanks Leah for her interesting and very clear talk. So let me say goodbye for everybody.
Yeah, thank you very much. And if you don't mind, please send your slides so that we will upload them.
Yes, will do. Thank you all so much.
Yeah,
thank you for having me.
Thank you. Very interesting.
Please just wait 1 minute. One of my postdoc would like to ask you a personal question about about China, something like that. His name is Ali Hadjiro. Maybe this is not questions for all people, but we can wait a little bit.